But since there was a video for the homework, I'll assume everyone did okay. But if not, just touch base with me after class. I put something up here. We're going to talk about right triangle trigonometry. So we're going to step away. Last class we were discussing angles, right? Just, you know, the whole definition of an angle. We determined that we have two ways of measuring them, degrees and radians. And then now we're going to step not away from it, but we're going to go to a different geometric figure here, and that's a right triangle. And from the right triangle, we're going to establish the definitions for the 6 trig functions. But before we do that, I thought I would ask this little true or false question, just to see what sort of responses I get. So what do you think? Does it kind of make you feel a little bit uncomfortable that I'm even asking it? Like maybe it's supposed to be false, maybe? Right? How many of you have heard that the sum of the angles of a triangle have to be 180 degrees? Yeah? You've heard that somewhere? Okay. All right, so do you remember when we were talking last class about the Euclidean plane and Euclidean geometry? No? Euclidean. When I drew the x-y axes, and I said two-dimensional space is called Euclidean geometry. It's all based upon Euclidean geometry. Well, this is true in Euclidean geometry, it's true. But I thought I would introduce you just to this idea, just to get you thinking. What does a triangle look like on a sphere? And we want to talk about a sphere because we live on a sphere. Well, the Earth is roughly a sphere. It's not exactly a sphere. But what does a triangle look like on a sphere? Does it look like the same thing as a triangle on a flat sheet of paper?
No, it has a curvature.
It has some curve to it, right? So let me give you an example. If I take, let's say, here's the Earth. Say that's the equator there, okay? And we start at the North Pole, and we head straight down to the equator, right? And let me do this in a different color. So we go and we follow the curvature of the Earth down to the equator, right? And then from there we move along the equator some distance, and then we head back to the North Pole. Right? Y'all see that? That would be a triangle on a sphere. And the sum of the angles here, there's curvature, first of all, it's not a flat triangle. It's curved. So, but we still define a triangle on a sphere to be this. And if we look at the angle here, what's the angle? What do you think we would say the measure of this angle is right here? You came straight down, and then you went straight over, right? So what's that angle? Like if you imagine walking from the North Pole down to the equator and then turning and going along the equator, what would that turn be? 90 degrees, right? This would be a right angle, 90 degrees. So we use that for a right angle. This is a terrible marker. I just grabbed it from the office. Yeah, I'll try that one. And then when we get to that other point on the equator and turn back up to go up to the North Pole, we're going to have another 90, aren't we? This is going to be another 90. There's another 90. That's right. They're probably all dead. Heads up, I could hit anyone in the class with this marker right now. All right. They're probably all dead, but we'll give it a shot. All right. Is it going to work? Oh, wow. Okay. All right, so that's 90. So already we're at 180, right? And then whatever this angle would be, this would depend on how far you walked across. So all I'm getting at is something that you'll hear this theme throughout the course, is that when we talk about geometry and we talk about, you know, things in this class, realize that we are living inside of a fishbowl of Euclidean geometry. If you step out of Euclidean geometry and go to spherical geometry, which this is called spherical geometry, then you have a whole different set of rules, right? So it's not just as cut and dry as this. That's what you're taught because that's what you're used to, but there's more out there than just this. FYI. All right. Now, right triangle. What is a right triangle? A right triangle is on a Euclidean flat sheet of paper, right?
It's 90 degrees consisting of another two 45-degree angles.
It just has to have a 90. That's it. Okay, so any triangle you draw that has one 90-degree angle is a right triangle. So it must have a 90. Okay, so that right there, 90 degrees. What's the radian measure of that angle? If I said, what's that angle in radians? 5 over 2. 90 degrees, pi over 2. All right, so any triangle that has a 90-degree angle in it, this is called a right triangle. All right, for every right triangle, there is a longest side, which we call the hypotenuse. And then the two other sides are the shorter sides, and we call these legs. So this is leg, this is a leg, and this is a leg. And sometimes the legs have the same length. Sometimes they have different lengths. If they have the same length, do you have any idea what the two angles here would have to be then? If these two are the same length, then the angles would have to be the same. They'd both be 45. Because you need them to all add up to 90, and these two have to be the same in order for these two sides to be the same. All right, but that's our right triangle, right? Now, when we have a right triangle, we can label the angles in here however we want. The common labels we use are theta, and then beta, but you can use pretty much any Greek letter, or you can use capital letters like capital A, capital B. The book does variations because in different textbooks they do different things. So I'll use theta most of the time for my angles. All right, so let's just get some terminology and just some understanding of the picture here. If I say, hey, what is the side opposite of the 90? You would be talking about the hypotenuse. If I say, what is the side opposite of theta? You'd be talking about this leg. And the side opposite of beta would be this leg. Okay? We all right with that? So what I'll do is I'm just going to put leg here. I'm going to subscript it with theta. And I'm going to subscript this leg with beta, just so you can make the relationship in your mind of which goes with which. Now, what can we say about theta and beta in terms of their size? If you're talking about a right triangle, what can you guarantee me about theta and beta? They add up to 90, right? Which means what? We know
the legs are of equivalent length, so both they'll be equivalent of one another.
Okay. Give me the biggest any of these two could be. Like, what would be the largest theta could possibly be?
89.
89? Okay, how about 89.5?
Oh, you're
Right?
right. 89.8 decimal.
Yeah, so let's try and say that. It can be as close to 90 as possible. Can it be 90 though?
No.
Can't be 90 because if theta is 90, then
There will be no
we have nothing left for beta, so it won't work. Less than 90, right? So can we agree with that?
Numbers less than 90.
Less than 90, and beta must be less than 90. This is a restriction we have for any right triangle. The other two angles have to be less than 90 degrees. Must be. Now, they could be any number up to 90, but not including 90, right? If I could include 90, I'd put the inequality sign, the bar underneath, equal. Okay? So anytime we have this, any angle between 0 degrees and 90 degrees is called what? Have y'all heard this? An acute angle. It's cute, right? It's cute because it's little, and like little dogs are cute, and little angles are cute, right? Then obtuse is bigger. But for right triangles, we don't have up to, so I'm not going to talk about them yet. Yeah. In general, if we take out right, then we can have a mixture of acute and obtuse angles. All right, we good? This is just language and getting some pictures in mind. All right, so now what I'm going to do is I'm going to redraw this. I want to follow the books. Yeah, they're using little letters. Okay, so I'm going to start over, another right triangle. And we are now going to set forth trying to generate the 6 trig functions. So the goal here is to define 6 new functions. All right. Now, let's make sure we understand what we mean by functions. The functions that you dealt with in college algebra, things like parabolas, right? Root functions. Yes?
Yes.
All of those functions took some input in and spit out some output, right? It took in a number, spit out a number. We are going to try and define 6 brand new functions right now that will be with us for the rest of this class into calculus and beyond, all right? These 6 functions behave the same way. They take in an input and they spit out an output. But each one of them does something different with the input, okay? Now the input that we're actually going to have for these is a number, but it is the measurement of the angle. So it's these functions take in angles and spit out numbers. And what we're going to do is try and see where it comes from, like what is it spitting out, all right? So we're going to do this by drawing a right triangle. And let's use capital letters. Capital letters for the angle, so I'm using that instead of theta and beta. And the side opposite of capital A is little a. The side opposite of capital B is little b. And then we're going to call this side over here C. The hypotenuse we're going to call C. So if somebody gives me a triangle, okay, so say somebody hands me this triangle right now, then I can define right now a relationship where if I take in the angle A, okay, oh, let me do it this way before I actually write it down. I'm going to define a function f, okay, that takes in the angle A, and what it does is it spits out this. Okay, now somebody explain to me in words what that function is doing.
You taking the value of A, that could be any value,
Mm-hmm.
and plugging it into the A over C function, which is going to give you out a function of A, or a function of B.
Okay, so if somebody gives me this angle, right,
Yeah.
then this side is defined.
Yes.
Like this is going to have some value to it. And so is this hypotenuse. Agreed? Now, this function takes in this angle, and it's spitting back to me a ratio, right? A fraction. And that ratio is this side of the triangle divided by this side. Okay, so if this is 1 and this is 2, then f of a would be 1/2. That's it. That's what that function does, all right? It always just takes the side opposite of the angle and divides it by the hypotenuse. I just chose that function out of nowhere, all right?
What is the output?
It's the side opposite of the angle divided by the hypotenuse of the triangle. I could have done A over B, right? I could have done C over A. I could have done C over B. I could have done B over C. I'm just choosing to define a function this way, all right? This function has a name. We call it the sine function. So instead of calling it f, we call it sine. And this is the way we write it. Sin of A equals A over C. Now, can somebody in words, instead of using A and C, give me the description of this side divided by this side in terms of its relationship to the angle? In other words, this side is the opposite side, right? Over this, which is the hypotenuse. Right? Opposite over hypotenuse. So I'm going to do this in blue. Opposite over hypotenuse. All right, which we can just say is O over P. If later on I'll use something O over H. I don't know why I put O over P. Okay. All right, so I just decided that if we draw a right triangle, I'm going to define a function f and call it this relationship, and then we have a special name for it called sine. All right, that's one of the 6. So what could be another relationship I set up? Give me this angle.
B over C, which would be adjacent over hypotenuse, which is cosine.
This one over this one?
Yep.
I could do this one over this one?
Which is cosine.
Okay, so we go I'll call it a different function. G of A equals, in this case, B over C, which we actually define as the cosine function, B over C. All these functions are doing, all they're doing is giving you ratios, a measurement of a ratio. That's all they do. Okay, you give me the angle, it spits back a ratio. Now, we call this side the opposite side, right? If this is A, this is the opposite side. The side that is the shorter leg closest to the angle here is called the adjacent side. You probably, most of you are shaking your head, you've heard that before. So this is actually the adjacent side over the hypotenuse. Adjacent over hypotenuse, which we will put A over H. All right, what have I not done yet? I can try, maybe I can mix up another one. A over B. I could do A over B, and this would be the opposite over the adjacent, and that's actually called the tangent function. So I'm going to stop doing this, okay? You get the idea? I could keep doing this. The next one would be tangent of A, would be little a over little b, which is, in terms of language, it is the opposite over the adjacent. And this would be O over A. All right, that's 3. We're halfway there. Yeah, so what if we took all these ratios and flipped them? So instead of doing A over C, we do C over A. And instead of B over C, we do C over B. And instead of A over B, we do B over A. Those are the other 3. So let me write them down. And so it's the reciprocal, wasn't that what it meant? Reciprocal meant flip over? So these are what we call the reciprocal functions for these. The reciprocal function for sine, anyone know it?
Secant.
Cosecant. It's cosecant. Cosecant of A equals C over A, which is the hypotenuse over the opposite. By the way, these are the abbreviations. I'll put up here the proper English word for this. Sine, okay? This is cosine, tangent. This is cosecant. All right. The next one is the reciprocal of cosine, which is the secant function, which would be what? C over... Yes, but in terms of the C and B, it would be C over B, right? Which is your hypotenuse over your adjacent. And the last one is called cotangent. And I'm running out of room down here, so I'm going to put it over here. I'll just squeeze it in right here. Last one is cotangent, COT. And that would be your, which letter over which letter? B over A, which is your adjacent over your opposite. And that's cotangent. Okay, so given a right triangle drawn with this configuration, we can define 6 trigonometric functions. These are them. These are called the 6 trigonometric functions. Now, the first 3 are the most important because if you can get the first 3 down, then these, you just have to remember reciprocals, right? Yes?
Yep.
So who has a cute little clever way of remembering the relationship between sine, cosine, and tangent? I know some of you have learned something.
I know, I don't remember it.
You don't remember it? SOHCAHTOA? How many of you heard SOHCAHTOA before? Okay, so I'm going to use this because it is very useful, okay? I still sometimes find myself using it. SOHCAHTOA. So SOHCAHTOA was this Native American girl who discovered right triangles. Her name's SOHCAHTOA. I'm kidding, but that's the story, okay? SOHCAHTOA. And this little Native American inventor of right triangles, her name just so happens to also help you remember the relationship between the trig functions. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if you can remember SOHCAHTOA, then you can kind of see it and you can kind of do this thing. Sine is opposite over hypotenuse. You see it? Cosine, tangent? Okay. If not, you just memorize it that way, however you want to do it. All right, so I have a question for you now. Now that we've defined these 6 functions, can anybody tell me, in terms of this triangle right here, what sine of capital B is?
B over C?
B over C. So you're looking at B, and you're looking at opposite over hypotenuse, right? Sine is opposite. So the side opposite of B is little b over the hypotenuse, which is C. So this would be B over C. How about cosine of B?
A over C.
That would be the side adjacent to B, which would be this one, A, little a over little c. Tangent B.
B over A over A.
So opposite over adjacent, B over A. And then we could do the next 3 would just be the reciprocals of those, right? All right. So the input, right, what goes into the function is the angle. Once you have the angle, then you can determine which are the sides. So I can't just ask you, hey, look at this triangle. You know, what's sine of this triangle? That's not enough information, right? I have to say sine of an angle. Sine of A or sine of B? All right. We good? Something else we need to know? I'll leave that up there. The Pythagorean Theorem. Okay, the Pythagorean Theorem is a very important theorem. It's used quite a bit. And it says if you have a right triangle, so you have to have a right triangle in order for this to work. And all I have to do is draw that, and now I've told you I have a right triangle. The assumption is that we're in Euclidean geometry, right? Because Pythagorean theorem goes away if you're on a sphere or something. It's no longer there, right? So the Pythagorean theorem tells us that if this side is little b, this side's little a, and this side's little c, that there's a relationship between those sides. And the relationship is a squared plus b squared equals c squared. In other words, if you have 2 sides, of a right triangle, you can always solve for the third side. You all got that? If anyone gives you two sides of a right triangle, you can always solve for the third. So let's do a couple of examples. We'll start off with very basic, and then we'll move our way to something more difficult. All right, how about this? As an example, find all sides. Now, this is not drawn to scale, okay? It's just 5. That's a very common right triangle, the 3, 4, 5 right triangle. And let's just make sure we understand how we would get that, because we'll need that as we move forward. If we are given a right triangle like this, then we could call this side little a and this side little b, right? And this side's little c. So we'll just label that little c. And then we'll use a Pythagorean, which would tell us 3 squared plus 4 squared equals c squared. And we square. And we get 25 equals c squared. And now what? Square root both sides? Wait a minute, though. I hope that in college algebra you were taught that when you take the square root on both sides, you're always supposed to do what? Plus or minus, right? I'm technically supposed to put plus or minus here, and then I'm supposed to get plus or minus 5, right? Is C? And this is where you have to start thinking about the difference between an algebraic problem and a geometric problem, all right? If all we had was this right here, if I started this out and I said, hey, solve for C, you would have two real number solutions, 5 and negative 5. But within the context of the geometric problem, C is a measurement of length, and C cannot be negative, right? So it wouldn't make sense. So we scrap one of the answers. So C is 5, but let's not forget, technically, algebraically, we have to have both. I wouldn't take off if you put both, but you need your final answer to be C is 5. So we know what A, B, and C are. Fair enough? Okay. How about this? Another example. By the way, 3, 4, 5, right? The hypotenuse is always the largest number. So 3, 4, 5 is an example of 3 numbers that work in Pythagorean Theorem, right? And they're all integers. 3 is an integer, 4 is an integer, 5 is an integer. If you have integers here and they satisfy the Pythagorean, then these are called Pythagorean triples. Just FYI. There's a bunch of, you can just Google Pythagorean triples and it'll just bring you up a list of all the Pythagorean triples. This over here is not going to give us a Pythagorean triple because one of the answers will not be an integer. This one right here, that's going to be a decimal. Let's see. So what's the relationship? We're solving for what? This side? Which we're going to call what? B or A. It's your choice. Doesn't matter. So I'll call it A. So I know that A squared plus 4 squared, right? You just need to make sure you understand where the hypotenuse is, equals 7 squared. And that means A squared plus 16 is 49. And then A squared subtracting 16, what's that? 33? Root 33. And that's it. We would leave it like this. Now I said it would give you a decimal, right? We're not going to write down the decimal unless we are asked to write down the decimal. We're going to leave everything in what's called exact form. This is called the exact form. Now, somebody on their calculator, go ahead and do it. And tell me what the
5.744.
Approximately 5.744. Squiggly equals approximately. This is called the approximate. Did we talk about that last class a little bit? Okay. Approximate. So unless I tell you otherwise, or the book tells you otherwise, always get your answer in exact form, because there's no error in an exact answer.
So, are you saying you would take points off either way, or?
I might take points off if you do this without ever showing this. You know what I'm saying?
In order order to
Yes.
get the approximate, you had to have the exact, so.
You're right, but I
But
mean, if
perhaps
you
you-
wrote a program on your calculator to, you know, because you could write a little algorithm on your calculator where you just plug in.
Do that.
Yeah, so I mean, as long as, I mean, no one, this,
Right.
I'm just saying, as we move down the road and we're getting answers, let's just always leave them in exact form unless the decimal is required. I mean, we will need decimals at some point, but exact is always the best answer. Okay, let's do another one. The first two examples I gave you, the first example, we got 5, right? The second example, we got root 33. Numbers, right? Can anyone tell me about the answer to this? Are we going to get a number? No. We're going to get an expression. That's what we're going to get. We're going to get an expression that still has a variable in it. Because we don't know what x is, right? If we don't know what x is, we're not going to be able to nail this number down. That's right. So let's call this c here. We know that 5 squared plus x squared equals c squared. So that means 25 plus x squared equals c squared. And now we take the square root on both sides, right? And when you take the square root on both sides,
Yep.
yes, no? Yes or no?
Yes.
Sure? Any no's?
5 plus or minus x.
Yeah, I was gonna say, at that point,
Because you're doing algebraic expressions, so you still need the plus or minus there.
So are we unanimous on yes, this is okay?
No, it's not okay.
We got a lot of people on the fence? All right, yes? Okay, so look, this, when I was a math student, I used to run into things like this, and I'd be like, I wasn't sure, you know? I mean, now I'm sure. I know whether or not this is right or wrong. But from your perspective, is it right or wrong? So give yourself an example over here to see if it works. So 25 here. Let's put something squared here that I can take the square root of easily, like 9. Right? Okay, is this equal to the square root of this, which would be 5, plus the square root of this, which would be 3? Is that equal to 8? Is this equal to this is equal to this? Because that's what this line says, right? That this is this? Do y'all see what I'm trying to do here?
Yeah.
Okay, if this is 8, then this better be 64 under here, right? Because the square root of 64 is 8, and that's not it. Right? This is incorrect. This is your answer. You can't do anything with that. Algebraically, there's nothing more you can do with that. You must leave it like this. Now, what you may have been thinking is this. That is 5x. Okay? Because between the 25 and the x squared is multiplication. And when you have multiplication, you are allowed to break it in to 2 separate square roots, as long as there was multiplication. But the addition inside prevents you from doing that. Math would be a lot easier if you could do this step, but you can't. Are we clear? Okay. All right, so c is square root of 25 plus x squared. That's what it is. One more, then we're going to move on. I'm doing these because I know for a fact in calculus 2, you have to be able to do this. Like, this is just something that comes up. So, give me the other side. So you want to call it A maybe? Yeah? Okay, let's call it A. So we know that A squared plus 5 squared must be x squared. And let's solve for a. Subtract 5 squared on both sides, so how about a squared is x squared minus 25? Agreed? And now square root. And when we take the square root, we get a is equal to square root x squared minus 25. And we cannot break that down any further, right? We're done here. So that's it right there. All right, your turn. I'm going to give you an opportunity to take 5 minutes to see if you can answer the following, right? All right. I'm going to give you two x root 3 and theta. Okay? And here's what I want. Find secant theta. All right. See what you can do in 5 minutes. And you can talk to each other. I don't mind if you help each other out. In fact, I would encourage you to talk to each other. If you have a question, I'm happy to come by and clarify something.
We have to find C.
Gotta find C first.
So that would be like 2x plus square root of 3.
Okay.
C2, and that cancels out.
You get doesn't cancel out. It leaves you, oh yeah, the 3, you brought it over. Okay.
Yeah. So
Are you solving for C or X though? Because C is the hypotenuse, right? So you're solving for C there?
So we have to solve for x.
Other than that, I think you're good. Hold on a second.
If you do it that way,
Yeah, just leave. You can just leave it.
is it okay to like rationalize it or something, or do we have to leave it right there?
You could put it into one root. Let me see your rationalizing. You could do that also. Yeah, it doesn't matter.
Doesn't matter.
That does not matter. We could. Yeah, that would be acceptable. That would be completely acceptable.
That too.
Yep, they'd both be okay. All right. Question. Did someone raise their hand here? No.
We're done.
Okay. What do you got?
Is that it?
What happened to the root 3?
Well, the root 3 will be here, but C would equal this, or would be equal.
Did you cancel the root 3s?
Yeah.
Oh, they can't cancel.
They can't cancel.
They can't. It has to be like this. Yep.
Oh, okay.
Okay, I think we're close enough. All right. I'm going to work through this, but I'm going to go kind of quick. All right. So by definition, secant of theta, according to our picture, is, if we label this C, is C over root 3, right? And we just need to figure out what C is. Agreed? All right, so to find C, we can use Pythagorean. We can say root 3 squared plus, and this is what I didn't see enough of walking around, was the 2x squared was not being squared properly. When you square 2x, you have to put the square root on both the 2 and the x. So you get 4x squared. All right, just be careful with that. I saw a lot of this. That is not correct. All right, so you square both the 2 and the x. So here, when you square a square root, the root and the square go away. You just get the 3. Here you get 4x squared, and here you have c squared. And now square root both sides. So square root here. And that's what you get. Now come back up here. C was that, root 3 plus 4x squared over root 3. And that would be completely acceptable as an answer for me. But it can be cleaned up. It can be, there's different things we can do to that.
I was right, 3.
One,
Get rid of the root 3.
how do you mean get rid of it?
Well, because you have 3 on both sides. You have a square root of 3 on both sides.
No, you can't get rid of it because this is, you're trying to figure out what is secant theta. Secant theta is this expression, which turns into this expression. You're not working with an equation here that you're manipulating both sides. Look, if you multiply both sides by root 3, it goes away here and it goes away here, right? And then you're telling me what c
You
is.
have a root 3 at the top and the bottom of the division problem. You could simplify that part.
You can't do that.
You could rationalize the denominator.
Yeah, you can't split this into 2 roots, okay? The top cannot be split into 2 roots. You cannot cancel, okay? Because there's addition under that root, you cannot do that. What you can do is you can rationalize the denominator, or I kind of like this one. If you have a root over a root, you can just turn it into one big root, like this. That's legal, okay? And at this point, I mean, you could leave it like that. I mean, you could now split it like this. All of these are correct answers. That's correct. Okay, so the main thing is to get to this, all right? That's the main thing. Okay, good. We'll do one more. Find all 6 trig functions of beta. That means I want to know what sine of beta is, cosine of beta, tangent beta, secant beta, cosecant beta, right? Cotangent beta, all 6. So let's see if we can find those out. Sine beta, cosine beta, tangent beta, cosecant beta, secant beta, and cotangent beta. Do you know any of these without doing any work? Without doing any other work, is there any of these that you can get?
Cosine.
We have, the 7 is what side relative to beta? That's the adjacent. We have the adjacent and we have the hypotenuse, right? Adjacent and hypotenuse is cosine. So I know cosine of beta is adjacent over hypotenuse. And I also know that secant beta should be the reciprocal of that, right? 10 over 7. Agreed? But to get all the others, I need to know this side, don't I? This leg I need to know.
Root 51.
So we can do the Pythagorean to get this one. So without doing the work, root 51. And I'll circle it, meaning that, that came from scratch work over here, SW scratch work. You did that work on the side, a squared plus b squared is c squared, and you were able to solve for this on your own, but that was not given to you. But once you had that, you now have the opposite, don't you? Do I need to show that, or are you comfortable? You're good?
And then you just fill it in.
You just fill it in, yeah. So sine, SOHCAHTOA, opposite over hypotenuse, so root 51 over 10. And then this one over here, we just flip it, right? 10 over root 51. I'll revisit this in a second because the square root's on the bottom. We'll talk about that in a second. How about tangent beta?
Root 51 over 7.
Root 51 over 7. That's opposite over adjacent. And then this one is the reciprocal. So 7 over root 51. Any questions? Somebody gives you 2 sides of a right triangle. You can always find all 6 trig functions. You're going to have to solve for one of the missing sides, but then you just set up all the ratios and you're in business. Now let me visit that topic. Okay, I did turn my microphone back on. I just want to see what the class reaction is to this. These 2 right here. Is it okay for me to leave those answers the way they are?
No.
No? No? Is it? Why not?
You can't have a radical on as the denominator.
Why not?
Because it leads to an irrational number. Or, that's not the right term. I know it's one of the rules you're not supposed to do it. I know that.
That's why I'm bringing this up.
I don't remember the exact term, but I know you're not supposed to do it.
You have been brainwashed, I guess. The brainwashing was effective because you're telling me I can't do it, but you haven't been given a good justification for why you can't.
No, I was. I just don't remember. It was like 4 years ago.
But there's no justification for it.
There is. I just don't remember it.
Okay, well, I'm not going to argue with you. I'm here to tell you that it is perfectly acceptable to have a square root in the denominator. I will tell you, so I'm here to unteach you some stuff that you may have been taught incorrectly because it was taught, it's not taught incorrectly, but people always stick to that rule. Can't have a root in the bottom. Can't, and nobody ever has a reason why. Because if you get your calculator out right now, well, how many of you who've been told that you can't, you would rationalize it so you would do this, right? This is what you've been told to do? And then that would become 10 root 51 over 51. So I'd like for you to get your calculator out if you have it and if you're interested in knowing. I would like for you to do that on your calculator. And then I'd like for you to do that on your calculator. And they're the same numbers. So why is that not okay then? It's the same thing as this, right? So what you've been told is you can't. Here's why you can. Number one, it gives you the same answer. But let me explain why it was taught that you can't do it that way. It's historical. There's a historical reason for it. All right? Maybe after I explain it, you'll understand why it got burned into people's brains not to ever do that. Okay, before calculators, before calculators, computations were done by hand, right? So let's say we run into this problem during a computation. Let's say we have 1 over root 2. Now that problem right there is going to come up a lot. 1 divided by root 2, it's one of our common angles on our triangle, or on our unit circle, which we'll talk about later. 1 over root 2 is going to just pop up, pop up, pop up. So imagine I had to figure out what the decimal value of that was without using my calculator.
Root 2 is an infinite number.
Right? Decimal approximation. If I had to do that, I'd have a really tough time. So again, years and years ago, students would actually have to memorize what the square root of 2 was within a certain number of decimals. And everyone back, 60 years ago knew that the square root of 2 was approximately 1.414. Okay? They just had to know it. So they would say that this is approximately 1 divided by 1.414. Now let's have some appreciation for how difficult this division is to do by hand. If I do this division by hand, on the outside of the division box, I put 1.414. Got it? Inside, I put 1.000. And then I start asking myself the question, how many times does 1.414 go into 1? I would say, it doesn't. So I'd say, how many times does 1.414 go into 10? And then I'd be like, I don't know. Well, how many times do you think? Maybe 7 or 8 or something like that. So then we start messing around with it, right? You'll see the difficulty here? Okay, now, take this 1 over root 2 and rationalize it. That means you're going to multiply top and bottom by root 2, right? You're going to get root 2 over 2, aren't you? That's the equivalent expression. Now, let's see what that person doing this computation has to do. By hand, they're doing what? What's root 2? 1.414, and on the bottom, they're dividing by 2. Now, check out the longhand division on this one. A lot easier. Look, 1.414 goes in here, 2 goes out here. Does 2 go into 1? No. Does 2 go into 14? Yes, 7. Bring your decimal point up. Then you'd start doing your stuff and you get 707. It's much easier to do by hand than this is. That's the reason why we rationalize, because we like our denominators to be nice integers so that when we divide in, it's easier than dividing in with an irrational number into an integer is hard to do. That's why. It's useless for us anymore. We don't need this, right? We have calculators. So please unprogram yourself to think that you have to rationalize things. Now, you should know how to, because the algebraic skill is necessary later, especially in calculus. But don't go telling people that you have to do it, because you don't. All right? So I very rarely will rationalize my denominators, very rarely. I'll only do it if I'm trying to match an answer in the back of the book, because the author of this book is going to rationalize denominators. Okay, it's going to happen. All right. Reciprocal identities. I was upset when I first heard that, I was very upset. Like, why did they tell me I couldn't do it? It makes sense. Do y'all know this? Back from college algebra, like when you have log base 4 of x, you write it like that. But when you have log base e of x, that we don't write it like that. We write it how instead? What's ln of x, right? Y'all know why we do that? I'll tell you. Because natural log comes up so much in research papers that back in the day when you used to have to use typewriters, this was like when typewriters were a big thing, or even nowadays, have you ever tried to subscript? Subscripting, when you're typing up in like Word or something. Subscripting is not super easy, right? I mean, there's a shortcut for it, but like typewriters, back in the day with typewriters, you'd have to like stop typing, like rotate the drum, and then rotate it back and then keep typing. And the natural log would appear hundreds of times within someone's research paper. So what they did is they said, look, let's just do this. You never have to stop typing, right? natural log x, you don't have to subscript. And same thing with log base 10. Log base 10 comes up all the time. So instead of doing that, we just do log x. That's it. Okay? It's these little things that we do in our mathematical systems that are appropriate for what we're trying to accomplish. Shorten the time, shorten the effort, right? But there's no other reason why we write these this way. There's no other reason. All right, reciprocal identities. Would you help me with this? Sine of theta is equal to 1 over, we talked about this earlier, that if we took those ratios when we were defining them, we could just flip them and come up with another trig function. So what was the one that we flipped to get sine? When we flipped sine, what trig function did we get? Cosecant. So we have this identity, that sine of theta is equal to the reciprocal of cosecant. You could also write it this way. Cosecant theta is equal to 1 over sine theta. And we can do this for all 6. So let's do one more, because I'm sure you could do this yourself, and they're in the book. Let's do tangent. Tangent theta is the same as what? 1 over what? 1 over cotangent theta. Or you could say that cotangent theta is 1 over tangent theta. All right. Now there's 2 more. You could do this for, well, I'll just be complete here. Cosine theta is 1 over secant theta. Or you could say secant theta is 1 over cosine theta. Right? But there are 2 others that are actually kind of important that you know. And that's tangent theta, by definition, was opposite over adjacent, right? Another way you could write this is as follows. You could write this as sine theta over cosine theta. Now let's try and understand why that is true. What is the definition of sine theta in terms of SOHCAHTOA? What's sine in terms of SOHCAHTOA? It's opposite over hypotenuse, right? And what is cosine of theta? Adjacent over hypotenuse. And if you take a fraction and divide it by another fraction, then they multiply and reciprocate. Won't the hypotenuse cancel? Yeah. And you're just left with opposite over adjacent, which is what tangent is defined as. In other words, this is the connection you need to make. Tangent theta is sine over cosine. Sine theta over cosine theta. And there's a similar one for cotangent. Cotangent theta is what then? Just that flipped, right? Just that flipped over. Cosine theta over sine theta. All right, these are our first identities. We're going to have lots of identities in here, lots of formulas to remember. These are our first set of them. Now what we're going to look at are what are called the Pythagorean identities.